the emulation platform that we are going to be using for these demonstrations is a tool called Renode, right? Renode is an open source software that it's a development framework, a software development framework, and it's from a company called Ant Micro. They have made the core part of it open source, which means that anybody can download it and use it, and you can also build sort of additional add-ons to various parts of the emulation framework, right? For our purposes, it helps us to sort of build models of an ARM processor combined with various other peripherals, and that's exactly what we are going to be using it for. It's able to emulate several different processor families, right? And usually what it focuses on is what is called instruction accurate emulation, right? Which means that the actual instructions, each individual instruction will be emulated in software, and you finally you are able to execute programs on the model of the system that you have built. Now there is another tool similar to this called QEMU, which has different sort of goals in terms of how it is built, but is also capable of actually building larger systems. In our case, we will be using Renode for our system level emulation work. It allows us to emulate a full system. What do I mean by a full system? Essentially, we can attach standard peripherals like UART, SPI and so on. We can also attach custom peripherals either through software extensions or by co-simulation with RTL. Now this co-simulation with RTL is a slightly advanced topic, but we will be looking at least some examples of that moving forward. For now, we are mainly going to focus on just system level emulation. So this is the website of Renode itself, right? Of course, as they have mentioned here, they they intend that you use it in order to develop IoT products, but it also tells you a little bit more about what the software as such can do, right? It allows you to develop, debug and test multi-node device systems. And as you will see later, they essentially provide you with a nice scripting language where you can create a system with potentially a common bus and multiple different CPUs connected to it, and different kinds of memory, different kinds of peripheral all attached onto the same system, right? And as mentioned over here, it essentially can give you full determinism of execution, right? Meaning that the execution you can literally get down to the point where you single step through the different instructions that are running on the system, right? And it provides excellent debugging capabilities as well, some of which we will see as we move forward. Now, one thing to keep in mind as far as this particular course is concerned, we require the use of Renode for a very specific purpose, which is to emulate some systems that we want to understand. We will not be getting too deep into advanced use cases of Renode, right? And we'll primarily be focusing on how can we use it in order to boot Linux onto a system and then do some level of emulation firsthand before we actually get on with implementing something on hardware. Now, of course, this is the main Renode website. It is also useful to look at their GitHub website, which actually shows that it's a very active project, right, currently being worked on. It also gives a little bit more about information about how to go about obtaining the software and installing it, right? I will be sort of showing some parts of it as we move forward, and the accompanying GitHub repository will contain all the basic instructions that are required in order to download and install it on a system that you have. I am primarily assuming over here, I am going to be showing all the demos assuming either a Debian or Ubuntu like system, right? So some of the commands being used for installing software are going to be based on that, but it's not very specific. It's fairly flexible in terms of how to install it, and enough instructions are given in most of the things. In particular, what I will be using over here is this I think it's the Linux portable module that I download and install, and then we are going to use this in order to actually run the system. So there are some standard instructions that we need to follow in terms of how to install the software, how to get things set up for the demonstrations that we are going to use, right? I am not going to walk through each and every one of these. As far as the demos are concerned, I already have these things set up, but the accompanying documents on the GitHub repo will also have fairly detailed information about how to go through each of these steps, right? So I would strongly recommend that you try these out on your own. You could just get a virtual machine with Linux on any computer that you have, or if you are of course running Linux on your system, then pretty much all of this should work out of the box, right? So rather than sort of focusing on the exact steps that are needed, I'm going to leave the pointers in the accompanying material and then focus on showing you how the software itself works. So the first demonstration that I'm going to give over here is just, how do I get a very basic, what does the basic Renode monitor look like? What does a Renode script look like? And what does a Renode platform specification look like? And then finally, how do I get a very simple basic program running on this platform, right? So before running Renode and showing you what the interface with Renode looks like, I'm going to start off by basically going through a very basic, the platform description and the script that is used in order to control the operation of Renode. So these files which have the .resc or Renode script extension are used in order to create simple platforms that we can use in order, or create simple scripts that basically allow us to run through the various steps involved in creating and implementing a platform, right? So let's look at what exactly this thing looks like, right? As you can see over here, what I have is, I start off by saying that I want to use a sysbus, and using sysbus is a standard system level bus description that is available inside Renode. All that we say when we talk about using sysbus is to say I want to create a new machine which uses the system bus, okay? So let's in parallel also walk through the process of what a system bus would look like. So in other words, what I have over here is, I have created something called a system bus, right? Now in practice, that system bus is probably going to be an AXI bus, but right now as far as Renode is concerned, I don't really care about the details of the bus. It could be an AXI bus, it could be other kinds of AMBA related buses. There are limitations on the kind of buses that it can emulate, and mostly where this comes into play is when you are trying to integrate with other kinds of peripherals. Why does that matter? Because it means that the actual signals that are available when you are trying to integrate other peripherals will be dependent on the type of bus that you use, okay? So what I have, the system that I am trying to emulate over here is something which has a system bus, and from that it has an ARM processor, right? To be more specific, it's something called an ARM Cortex A9 processor, okay? Now what does this ARM Cortex A9 processor mean? It means that I am creating a system where I have a bus and there is one processor that's being attached to it, right? In addition to that, it also has a certain amount of memory, and as we will see, I am also attaching something called a smart timer. Okay. So as you can see with a picture like this, effectively what I have is, the bus is what determines the overall structure of what I am trying to emulate, right? The CPU is one of the components attached to the bus, of course arguably the most important, but the memory is also very important, otherwise you won't be able to you won't be able to load programs and do anything useful with it. The smart timer is actually optional, right? I'm just attaching it over there to sort of show that you can actually create custom peripherals and attach them. So let's look at how this comes across in the Renode script. So as you can see over here, in the Renode script, I first I use the system bus and I create a machine. So this mac create essentially creates a fresh machine, and now I do something where I basically say load platform description, okay? So what do I mean by load platform description? It turns out that these kind of file names, right, things like the smart timer _arm.repl, anything ending with repl usually is a Renode platform description, right? And the syntax is a bit peculiar here. It basically shows an @ which basically indicates that search within the known paths, right? So if I just give @ and smart timer arm.repl, it turns out that it knows that it needs to look in the present directory, but as we will see later, it also knows how to look in other directories that are not directly under the present directory itself, Okay, so there is some kind of the equivalent of a Linux or Unix path associated with it, and when I start with @ it means that I am referring to a file and it will search through that path in order to find a suitable file. Now let's go in and look at what that REPL file looks like. Right, and this one here, right, as you can see the syntax is slightly different. You might have noticed that in the case of the REPL script, starting with a hash indicates that it's a comment, okay, whereas in the case of the, or rather in the REST script, that is the Renode script, starting with a hash makes it a comment, but in the REPL file, that is the platform file, I use more like the traditional old style C comments, right, /*//, right, and effectively what I have done over here is I have built something on top of a model that already existed, right, which was basically using this something called the versatile express Renode platform. But what I have done is I have simplified it immensely. In this case all that I have is, you can see that I have a CPU, right, I also have something called system RAM, right, which is, as you can see, it is defined as memory.mapped memory. Okay. Now this memory.mapped memory is something Renode specific. It basically says this is a type of memory. It is also mapped onto the system bus starting at this address, right, 0x80000000, right, and it also has a size over here of 4 million hex, right, which is essentially, you can convert this into the equivalent decimal if you want, right, but it's like a few megabytes of RAM that we are talking about over here, right. The interesting thing of course is, as far as we are concerned, so system RAM in other words is a memory that is mapped on the system bus starting at this location with a size of this many bytes. The traditional way of expressing everything is in hexadecimal, right, because it's usually easier to manage memory maps in terms of hexadecimal numbers. As we have already discussed in the past, the reason for this is because the hardware decoding becomes easier, right. It's not that there's anything fundamentally great about hexadecimal numbers, but from a hardware point of view they are much easier to use. Now that's the system RAM. Now I also have something called a smart timer. Now the problem is I have not actually implemented a smart timer. I don't have Verilog code for it yet, or rather I have it but I have not integrated it into my system yet, and I don't want to talk about co-simulation at this point because that's more complicated. So instead I'm going to cheat slightly over here and say that my smart timer is also a memory mapped system, right. So my smart timer is also a memory mapped system which is now attached to the same system bus but at another memory location, right, starting with 0x7000 and 000. You will notice that these two memory locations, right, the addresses are non-overlapping, right. How do I know that? Because this one starts at this particular address but has a very small size. This one starts at a higher address which is definitely after this 7 followed by 7 zeros plus whatever size it has, and even though this has a larger size associated with it, it is still not sort of occupying the entire region of memory that is available to the system, right. So both of these things are sort of modeled as mapped memory to start with. So let's quickly go back and take a look at what that means in terms of our system diagram over here. I can now think in terms of a memory map, right. I have my CPU, and what the CPU says is, starting from this location 0x7000 or whatever that number is, right, plus some size which in this case is 0x1000, that much hexadecimal. This corresponds to the memory map for my smart timer, right, which right now I am sort of cheating and just implementing it as yet another memory block, right. In addition to this, I also have a memory block which is somewhere up here, right, which is my system RAM, right. It starts at 0x8000 and goes up to this plus 0x 8 3 this final value. How do I know this final value? Because of the size, right? I know that this was given as 4 and I think 6 zeros after that, right? So if I look at it and put the thing correspondingly over there, I'll see that the very last address that I have over here will be 83 followed by 6 Fs, right? So that's the range of addresses corresponding to RAM. Any location that I go in and check as far as that is concerned, I'm going to find that this corresponds to the memory of the system. Any address within this range, right, should tell me that it corresponds to my smart timer. What about the remaining addresses out here? Well, nothing really, right? I don't have anything mapped in any of these places. This is a very simple system that I'm starting with. So now that we have seen what the platform description looked like, right, in the smart timer.REPL, we are now going to just basically set up the rest of the system. I can specify a logging level, which is useful for giving me additional debugging information if I need it. I'm also going to put in a couple of sort of helpers over here. One of them says that when I'm running on the CPU, any function name that gets executed according to my code should get logged. Now this is interesting because finally what I'm going to be running on that CPU is not really a source code. I'm not going to take a C program directly and run it. I'm going to take a C program, convert it into an ELF file and run that on my final system. It turns out that ELF files still have embedded information within them that tells the names of functions, and it is possible for Renode to identify branches as function calls and find out which function is being called at this point in time and to print that out. Okay. This is not as trivial as it sounds, because at the end of the day what Renode is doing is actually emulating the system at an instruction level. It is not going through your C code and running it. It's looking at the output, compiled output, running that, and in the process it's able to pick up that these kind of branches actually correspond to some kind of function calls and print those out. Right. Similarly, we also have a note over here telling it to log all peripheral accesses. We'll see that in a moment. It can be useful for debugging. The other important thing is that I actually am going to load an ELF file. What's an ELF file? It's basically an executable in the ELF or extensible linker format output. Okay. We'll look at the C code corresponding to this in a moment, and then we'll see how that gets converted into an ELF file, right? But the interesting thing is Renode is able to take the ELF file and load it appropriately into memory. Now it's kind of interesting, right? Remember that when we are finally executing a program on a CPU, this is bare metal, right? There is no operating system currently in place. So I need to specify exactly where the instructions corresponding to my program get loaded, right? And I have to do it in such a way that when my system switches on, my program counter is going to start with that value that basically points me at the correct place. Okay. So what are all the things we have in order to help us with that? One is we have chosen a certain model of the CPU, right? It basically says it's an ARM V7A, in particular the Cortex A9. I have also specified where my main memory is. It starts at this particular address. What that means is that when I load ELF, right, the ELF file will actually contain information about where it expects to be loaded. Right? If it's a bare metal ELF, then it will basically say, okay, I need to be loaded at this particular memory location. And what the load ELF will do is it will basically take that and load it into an appropriate location in the memory. Okay. Now all of this is handled transparently by Renode. So as far as we are concerned, let's get on with how do we actually make use of this.